Okay, welcome to Thermodynamics. Couple housekeeping items. We're just doing our test on Chapter 8 and Chapter 7's worth. And it says, oh yeah, on Monday, Chapter 9, first, like superhuman homework to do, but I'm thinking maybe we put that one off about a week, something like that, which makes it due right before Thanksgiving, like the Monday before Thanksgiving, something like that, because I haven't done any examples, so yeah. And then the week after that, the first of Chapter 24 will be due, and then there's two parts to the Chapter 24 homework, and the second Chapter 24 homework would be due at the final, which is how that all worked anyway, but now we're just kind of, yeah. So that's what I'm thinking on schedule-wise on all that.
So Chapter 9, next, not this coming.
Correct. Yeah, so we have some time to talk about it, and like, because I know everybody's like focused on Chapter 7, Chapter 8 for the test today, there's examples. I'm going to just talk story on these engine things and then come back and work the examples starting Monday. So we don't get too much stuff confused, hopefully. So any other questions? It seems like there was some other questions.
I do have a question, homework for 8, but before I ask that, is it final on cumulative?
Approximately. I mean, why is it cumulative? First we talked about what is a property, and then we talked about what is a process, and then we use it into, go into the engine cycles and things, which is what it's all about. And so, yeah, it is because you use all that stuff. So, what it's really about is Chapter 9 and 24. But to do Chapter 9 and 24, it really is building on all the other stuff. So it's going to be about Chapter 9 and 24.
Good.
Yeah. Because, you know, really what comes down to all the stuff that's leading up to it is just so we can talk about what's in. Chapter 9 is all about engine cycle. Chapter 24 is more about like heating, ventilating, air conditioning, refrigeration, and the loads that happen due to moisture in the air, and how do we figure that out? And those are all dealing with all the stuff we've been. So yes and no. It's all about 9 and 24, not cumulative, but 9 and 24 are in themselves cumulative. Anything else? Had some questions on these engine cycle things. What about this network thing? There's usually work coming out, and there's work you have to do to make it go in. You have to have a compression stroke. So, you know, somewhere if you have a two-cylinder engine, while the power stroke is coming down, there's a compression stroke going up, and the amount of power you get out of the crankshaft isn't the amount of power in the power stroke. It's the power stroke minus the work that it's doing on the compression stroke. So that's the network thing. And all cycles have something you have to do to keep it going, and then you're getting more power out of it, but you have to make up for, you have to subtract from that the amount of work it takes to keep the cycle moving. So that's what that is. The network makes a difference. Your efficiency is based on what do you actually get out of the output, not just what do you get out of the power stroke or the turbine power. The turbine has to turn a pump somewhere, so and gas turbine has to turn a compressor, and it turns out the work ratio on a compressor, the compressor for like a jet fighter type engine is like 100% of the turbine work goes into turning the compressor. It's like there's no efficiency there because it's not turning a shaft, it's getting a thrust. So, you know, your work in could be 100% of the work out. You got nothing to show for it, except like supersonic fighter jet. But anyway, yeah. So that's It's the network thing. So, and that, on the test, that one of the questions will be, what's the efficiency? Remember, not just here's the work out from a enthalpy of a turbine or something. If there's work going in, that matters. We were talking about the diesel cycle before. Difference with the gasoline engine is you have an air-fuel mixture, and as you compress it, it gets hot. And if it gets too hot, this starts burning before it's supposed to, and it starts pushing against the piston as it's coming up, increases the work in your compression cycle, compression phase, which takes work away from somebody else's power stroke. So you don't want it to go off, so you're limited by how much compression you can do when you have an air-fuel mixture. Diesel, from the get-go, started off compressing it enough to the point where the air at the top of the compression is hot enough to start combustion. The molecules in the air are whizzing around so much that when you spray the fuel in there, it knocks them open, and then they recombine. And that's how I think of it on like a molecular scale. And the way you start your combustion is to add some fuel to the air, so you can have a high compression ratio. There are cars just in the last couple of years that are doing this with gasoline. First one I remember hearing about was Ford. And I started off with Lincoln because it's low volume and they can afford the extra money. Question?
So do you only need like a glow plug to start the engine once it's hot enough? It doesn't need that.
You don't even need a glow plug if it's warm enough. If it's too cold, then the glow plug makes a hot spot. So the temperature of the air doesn't quite get up there, but the work in the glow plug it does. And then poof it goes. So yeah, most diesel engines, so it's asking about glow plugs. Most diesel engines actually have a little heater that, like this morning, I have a diesel Volkswagen. I went and turned the key, and it's like all automatic. It used to be you turn the key, and there's this little thing that looks like a pigtail. It looks like a filament, and it would sit there and it would glow. You'd have to give it a couple seconds, half a minute on the worst case, to heat up, and then you'd start cranking it. But if you crank it before that happens, you have to extra crank it, and then it will also damage the glow plug to have all that going on. And now I notice it's automatic. I turn the key, and I say, why isn't the car starting? Well, it's got the glow plug. It automatically waits until the glow plug cycle's done before it engages the starter. And that just makes an extra hot little spot. There's a little bit of air around it that's warm, and then when everything gets compressed, then there is a spot that's hot enough to start the combustion, and then it all works, and then as it comes up to temperature, it's fine. So there's our cold limit. There's also some interesting issues with the air-fuel mixtures. This is like not ethanol. If you run pure ethanol, like these days, the Indy 500 is changed to running on pure ethanol, I believe, which gives the engine more power than gasoline, but it's actually less power than it used to be because they used to run on methanol. And ethanol, at cold start on ethanol doesn't happen because you spray the ethanol in the air and it extracts so much energy in vaporizing it, because vaporizing your fuel in the carburation and intake will actually cool down the air charge, and if you cool it down to the point where it's saturation temperature for your ethanol or whatever your fuel is, then it doesn't vaporize and it just gets wet on the surfaces, and you can condense enough out of your air-fuel mixture that there's a flammability limit. You have to have enough fuel with the air so that if one of the fuel molecules go, it will hit another fuel molecule and you get a chain reaction. If there aren't enough of them, it won't sustain the chain reaction. The same thing on the other side. You have to have enough fuel, but if you have too much fuel, it floods it to the point where it breaks apart, hits another fuel molecule, but there's no air around the fuel molecule, and it doesn't sustain it that way. So there's flammability limits, both on the upper end and the lower end. For cold weather, if you condense fuel out of your intake, then it won't start because you're below the flammability limit. And it doesn't sustain the chain reaction. So with ethanol, cold starting ethanol, you can get to the point where fuel starts it to the point where it condenses out and it's too cold to start. It just won't start. So they don't make, they don't give you 100% ethanol fuel typically for make it available to consumers for two reasons. Number one, if people try to drink it, I mean, ethanol, it's a wash, right? It's, or, you know, it's 100% in theory. Ethanol is alcohol. So they denature it, they poison it with gasoline, which also makes it possible for it to cold start. Because if you get 15% gasoline in there, then the gasoline will vaporize enough to start, and then it warms up. And so we see E85 is the maximum ethanol, 85% ethanol, 15% gasoline. Or that's you know, there's the flow flood thing, and there's the fuel star issues that you have, especially with the renewable, with ethanol, the gasoline renewables. Yeah. In the diesel cycle, and again, someone was asking why you call S. There's a 2S that I'd mentioned sometimes, or a 4S process. This whole entropy tells us the limit of how much energy is available to be converted, or how much the minimum amount of work needed to get the work done. On a reversible process, yada yada, it's a calculated ideal limit kind of a thing. So if we're using, especially when we're analyzing these and we're using a formula that has a K in the exponents somewhere in there, that was derived using isentropic relationships. So it's going to be an isentropic value for the ideal gas. We're just using formulas. Remember, we're not using tables. Today you're going to have a steam one. The same concept. If you have a steam turbine and it starts off at some value, high value of enthalpy, there's a corresponding entropy value for it. The most energy it has available to convert will be a value at the new pressure that has the same value of entropy. If you can find where on that pressure, you know, in the saturation zone, where that has the same value of entropy, then you can find the value for H there, and that's the maximum amount that's available to be converted. The real turbine might only convert 90% of that. So if it started up at 1100, it went down to 1100 kilojoules per kilogram worth energy in the steam, and it comes down to a value, and it ended up on that, you know, some amount of quality. It's starting to turn into fog. If that value is 100, so you drop an enthalpy of 100 that has the same value for entropy as the high value. That says you could have possibly converted 1100 minus 100 gets you 1000 kilojoules per kilogram. The turbine it doesn't have more energy than that available to convert. If it was a perfect turbine, it would get you that much work. But if it has a isentropic efficiency of 90%, it says it only used 90% of that total value. So it would follow that pressure curve out somewhere to the point where the enthalpy would be, well, it only used 900, so 1100 minus 900 would be like 200 kilojoules per kilogram instead of the 100. It left 100 kilojoules per kilogram on the table because various things, it can't meet the isentropic, you know, reversibility thing where it's quasi-equilibrium, it moves so slow you can't tell, and all that stuff they use to define the entropy things. Oh boy. So where was I? Same thing here on the steam tables. It's about looking at the table. Entropy at the top at one stage is the same value at the other for the isentropic, and I'll note that as the next state, well, not state 1 to 2s or state 3 to 4s or whatever it is. That's that calculated theoretical number, and then the real number it'll say like state 2a. So in this case, if we're calculating this on a now we're talking ideal gas, and we've got two worlds. There's phase change world, and there's ideal gas world. In the ideal gas world, that would be state 2s. The real state would probably be slightly different. What's real would be the pressure. It would be somewhere else. This curve probably didn't follow this curve exactly. It has how would that work? The final state would be would vary from that. When we get into the calculations, we'll calculate and see how that looks. So anyway, diesel cycle is the main difference. Instead of a constant volume heat addition, it's a constant pressure heat addition. You start the burn happens slow and it chases the piston, and if you inject the fuel at the right speed, then because there's an amount of time it takes to push all the fuel in there, and if it's going at a speed that's right, then it will essentially burn and maintain the pressure as the piston is moving, which normally, as the piston moves, pressure goes down, but as the fuel goes in, the temperature rises. It's maintaining the temperature essentially until the fuel stops burning, you stop injecting it, and stops burning, and then the pressure drops. That's how we analyze the ideal cycle. And the real cycle is going to be like, 50% is good or 80% is good as the ideal. Effectively, this cutoff ratio thing was how you define essentially how much fuel you're throwing in there. And if the cutoff ratio was the volume from the start from 2 to 3, if from 2 to 3 there's essentially no volume difference, that's sort of what goes on with that's like comes back to an auto cycle. If this is 1 to some power, 1 minus 1 is 0, and then whatever else goes on here, that makes this equation go back to the auto cycle efficiency. As you put more fuel into it, the volume doubles before the fuel goes out. The volume triples before it goes out. The clearance volume to double that volume. As you put more fuel in there, this curve starts dropping off, so you're actually getting less efficiency. But the thing about it is, this is the range of, and it's actually more up into here. This is kind of the range at which diesels operate. And this is the range in which auto cycles operate. So compare this in here to these over in here, where net effect is your diesels have an inherent higher efficiency. And in reality, they'll get about 30% better fuel efficiency. So we're actually looking at basically 4 engine type cycles in this chapter. Auto cycle, gasoline engine; diesel cycle, diesel engine; Brayton cycle, which is a gas turbine, and then we'll take it into Rankine cycle, which is a steam turbine. And then the Rankine we can branch off into forwards and backwards. The backwards Rankine cycle is basically what's going on in the refrigeration system. So I'll do the examples later. Brayton cycle is different. All three of these, the Otto cycle, diesel cycle, Brayton cycle, those are all ideal gas. So we're all using the ratio of volumes or pressures to some exponent with the K in it. And if you got an exponent with a K in it, you're doing an isentropic analysis. And this air, the idealized, we're talking about air standard, just to simplify things. It's that air goes in, air goes around, and it's a closed cycle. So we have air, say we start here, we want air here to be at essentially room temperature and room pressure. And we take it into a compressor and compress it and compress it and compress it until it comes out, and then it comes out at high pressure. So there's a high pressure zone and a low pressure zone. Pressure gets nice and high, and then we put it into a heat exchanger, and in a warm environment, heat exchanges into the air until it gets up to the temperature that we want for the inlet of the turbine, and now it's both at high pressure and at high temperature. And then the turbine takes it and it expands, but what's it really doing? It's coming at high pressure, and it goes against the blade and blows it, and the blade turns it, and it's that motion, what's really going on is it's an impulse of it, a mass, flow rate, velocity change, direction, force, action, reaction kind of thing inside there. But basically, how you do that, we don't worry about that at this point. What does happen is it expands, and it starts off with a certain amount of energy here, and it comes out with some energy there. This would be an isentropic expansion. It's going to be an isentropic compression. When you analyze it, the air comes around and it goes into a heat exchanger. Now it comes out at low pressure and high temperature. And the heat exchanger just magically wait around until it comes down to air room temperature, make the heat exchanger big enough, and then around and around it goes at some mass flow rate all through there. That's how we'll analyze it. Now, at 30,000 feet on the wing of a 747, that's not how it works. At 30,000 feet, the air comes in through the nozzle. It does have a compressor. It does have a combustion chamber adding heat. What you do is you add fuel. What comes in is air, and what comes out is air plus fuel combustion products, which would be CO2 and H2O. Usually they run this at, in reality, at high excess air values, and they're heating up a mass of air. They're using the fuel to heat it up, but there's lots of extra air in it. They're not burning it all. And then it comes to the turbine at high temperature, high pressure. This pressure, but now it's got high temperature and now it wants to expand a bunch. And as it expands through the turbine and back down to the low pressure, it generates work. Now, if you make this work net go to zero, then the temperature and this comes out at is going to be high, and if you force it through a small nozzle, it goes fast. And that's what happens with a fighter jet. You just take enough energy out of it to run the compressor to keep the system going, and then it makes what Newton said, force equals a change in momentum over time, how fast, which is basically mass flow rate times a change in velocity. He didn't say F equals ma. We always call that like Newton's thing. This is what he really said. And if the mass is constant, then you get m dv dt, which is force equals mass times acceleration. That works for a rock. Constant mass. What if you have a mass flow rate? You take the same thing, I'm going to dissociate, now I'm going to say dm times dv over dt. That's another way to write it. And in fluids, we use that a bunch. dm dt, a mass flow rate, kilograms per second, times the change in velocity. That's what makes your garden hose whip around. You know, if you put a nozzle on the end of your garden hose, it kind of comes up through a hose that's 1.5 inches in diameter. It gets there and suddenly it goes through a 1/4 inch diameter, and all that pressure is potential energy turns into velocity. And there's a change in velocity right at the nozzle at whatever mass flow rate. The hose is delivering the mass flow rate with some pressure, and you turn that potential energy into kinetic, and the end of the hose it starts whipping around because you're not guiding it anywhere. If you're anyone like do volunteer firefighting or seen the training for that sort of thing, when they get a hose, you don't just give a guy runs off with a hose and okay, turn it on, I'm going to shoot this hose 200 feet. It knocks you over, beyond knocks you over. They'll have 3 or 4 people holding the hose and one guy steering it and 3 people holding it. Or they'll have it mounted on something and a water cannon. It's like a cannon, it really is. You either have to mount it or have 3 or 4 people holding the hose. A bunch of them are just dead weight, and then the one guy's kind of waving it around wherever it needs to go. So anyway, that's the sort of thing. This a change in velocity, and that's a change in direction. It doesn't have to be going from fast to slow. If you just take it down, you go and change in velocity in this direction, you got none in this direction, suddenly you change it all in that direction, you're going to have force both in the x and y direction to deflect it. So that's what goes on inside the engine. And the pressure difference in each stage is what keeps going through. So, you know, sometimes they do get networked. If you look at, I don't think I put pictures in on it because we got so much stuff to cover. But if you look at 737, you know, any commercial airliner that has a turbine engine, a turbo fan, they actually take this network output and they have a high bypass ratio where it's actually a big propeller in front that's ducted, and it's like this big around, and the turbine engine's about this big, and out of the back end the hot gases come, but you can trade off. If it's more effective to take some power, and instead of just, and that's actually kind of different between military and otherwise, you can get the same thrust. If I can increase the mass flow rate by putting taking a shaft out front and putting propeller on it. So that's like the regional planes. They'll have a turbine engine turning propeller. That's a turboprop. If you want to get more efficient, you put like 99 blades on that, put it inside a duct, and you have what they call high bypass ratio turbo fan engine. You have a fan in the front flowing a bunch of air, big mass flow rate, at the expense of the velocity. So you can't go supersonic with like an engine from a 737, but you can be more efficient and quieter. If you need to go supersonic, you need this. So instead of using the power to blow a bunch more air past the engine, you just you live with it and use your velocity to get the change of air coming in and then comes shooting out the back faster. It's noisy and it'll go faster. So right in here, it goes from being just air to being air plus the combustion products, and properties change a little bit. For our purposes, we're analyzing things with consistent properties, and that tells us what matters. We can analyze it this way. I don't know if we get into analyzing it that much, but one of the difference things now is it starts. Here's what on a pressure volume diagram. It starts with a specific volume of the. Now we're not talking about pistons. Now we're talking about specific volume of the air going through there. And Shelby?
So on the other slide, are you saying that we're kind of more focusing on the first picture and not so much the second picture? Is that what you're saying?
Not so much about the pictures.
Well, I mean, like the analysis that's shown in the picture. This one.
Yeah, no, it's this is ideal analysis. This is more real in any case, whichever one you use. If you want the engine to go faster, you leave more energy here and you don't extract as much here. So that would be like the jet fighter, high speed, high velocity this would come out hotter. If you want the turbo fan, is that what you're talking about? Those two, like the commercial jet engine, you'd extract more energy out of it, get some work, use it to turn a propeller or turn a big fan. It increases the mass flow rate around the engine, which then blends it back in with the exhaust, which was going slower now, but now you've increased the mass flow. It doesn't all go through the engine. Some of it's going around, not burning air, and then the two connect together at the exhaust pipe. And the fast speed gases here blend with the mass flow rate coming through, and everything comes out. The energy gets blended back together, but now you've traded mass flow for velocity. But both of those would have to do with this diagram. It's just, are you emphasizing shaft work coming out here and using it to blow more past the engine? Or are you leaving more energy in the exhaust gases to go faster and not use the work to increase the mass flow?
So then could you use that fan on the front and show it all in and like supercharge it, technically? And then go even faster? Yeah, you could. With the limits of the materials and stuff?
But then you just talk about you have a bigger turbo jet engine as opposed to a turbo fan. You could. Usually, actually, what goes on? There's so much excess air because they're not using as much fuel as they could. The real limitations you have are all the turbine blades they will melt. You can put enough fuel to melt the engine, so you're limited by those temperatures. But
So you're limited by the materials.
It's always, yeah, you're always limited by the materials. So yeah, you could blow it all in there and jack up, make it 1,000 psi in there, and you run it at 4,000 degrees Kelvin, and you have this flaming red ball of hot metal.
It isn't propelling you anymore.
No, it's kind of melting and dropping out of the sky. Yeah. So that's usually material limits. What they will do is if you get the air fuel coming out and it's at a high temperature, there's something called afterburners.
They can reignite it.
They use the excess air to add some more fuel, and it comes out under pressure, and you have a nozzle, you reignite it, and if you add fuel in there, it makes it hotter. What's that mean? Ideal gas law says if you got the same pressure, then your volume increases, but you have a mass flow rate that's constant. So if your volume increases with a certain mass flow rate, if your density goes down because your temperature went up, then it'll have to go faster to go through the hole to maintain things. So you have nozzles that you can then close up, or open up and add an afterburner, and then suddenly it's going faster. But now it's not melting the blades, and you can cool the nozzle on the outside, so they'll take some of the slipstream air, and they design it so that some of the air, cold air, comes around the outside of the nozzle to cool it from the outside. And then that heats up that air, which becomes hard at all. So that's what afterburners are after this, not part of the turbine cycle. The SR-71, which is, that's not a good picture of one, but that was like one of the more incredible manned airplanes. They don't make manned airplanes like that anymore, they don't need to. But the engine for that went Mach 3, and at Mach 3, I think the engine itself only provided 15% or 20% or something of the power at cruise, and the afterburner was providing 60%, and there was ram air, so you know, can you use that? They used the inlet to generate high pressure air, bled off what the engine didn't need, reintroduced it around the afterburner, and then that jacked up the afterburner pressure, and it was just the inlet, messing around with the inlet became like 30% of the recapturing kinetic
By
energy.
using the inlet as the compressor, basically?
Yeah. And there's issues at supersonic, you get shock waves, and you get standing shock waves, and how you design those to be effective is way eaten over my head. That's not something I've studied, but if you look up SR-71 inlet or SR-71 engine, there's like presentations about that now that was, you know, when they were designing that, you know, the new cars in the showroom were like 57 Chevys. So it's, you know, now we're talking, you know, 40, 50 years. So it's kind of been declassified. It was pretty crazy stuff they were doing. So cycle-wise, to go from state 1, which was the inlet, to state 2, pressure volume, we're compressing it so it's getting, the ratio you have on that now is a pressure ratio, and it's a ratio of pressures, not a compression ratio, which is a ratio of volumes. So this is all about pressures. And we use that, and if you go through all the numbers, this is how much it compresses, pressure-wise. The pressures are what's real, temperatures jack around. So it comes up to the new pressure, and then you add heat, and it expands gets to a new temperature. In this case, and the compression here is a isentropic, S equals constant, that says isentropic compression, and we have an isentropic expansion through the turbine. Q in is going to jet up, that's what it looks like there. The pressure is constant, but as on the TS diagram, temperature entropy, temperature rises, no doubt, you just put a bunch of fuel in it. And then it expands in the compressor, isentropic, or this way, it looks like that, down to the pressure that's, you know, exhaust pressure. If it came in at atmospheric pressure, it's going to leave at atmospheric pressure, but it comes out hot. Your exhaust comes out hot. That's energy that you then have to reject. So in the air standard world, we put it into an air conditioner or a heat exchanger and wait until it gets cool enough, blowing air across the heat exchanger. In the real world, it just blows out into the air and uses the entire world as a heat exchanger, and then over there on the other end of the engine, we suck it on in at standard temperature, whatever atmosphere it is. So it's a constant pressure heat addition, a constant pressure heat loss, exhaust, isentropic compression, isentropic expansion. It's an air standard cycle. We're using ideal gas. So there's going to be, between here and here, it's a ratio of pressures. And the amount of enthalpy between those two is C sub P delta T. And what's the delta T? Well, we're going to find out with that isentropic relationship that's it's going to have some exponent K in it, K minus 1 over K, or K minus 1, or something like that. And when you do those all around, the ideal air standard perfect world efficiency of it is going to be related to the pressure ratio. Now, that's about the efficiency. There's also an issue if you want it to do something. You can make something that's incredibly efficient, but it doesn't really do much. You want it to have a power output, not just an efficiency. You know, you've got this $10 million thing, and it puts out enough energy really efficiently to light a light bulb. Well, that's not a good thing. Maybe you'd sacrifice some efficiency in order for it to light up an entire city. So if you think about this TS diagram, remember P times dV is the amount of work, and this is the work that's being done. This diagram basically is how much work gets done. Up here, that's the top there is the heat in, the bottom is the heat out. The difference between them is heat that's missing, and the heat that's missing is equal to this. So T times ds equals heat, and that's the heat missing that got converted. Ideal first law says what goes in must come out, essentially, and it either comes out as heat or as work. If heat's missing, it came out as work. So this is saying we got a pressure ratio of 15. What's that mean? We had to add constant entropy. It went up to a high. The temperature is correlates with pressure. It went up to a high temperature. We added a little bit of fuel, and then it came down. And this is how much heat is missing in the cycle, how much work got done. You could make this pressure ratio go up to 20, and boy, that says we'd get more efficient. But if this went way up here, this area gets smaller and smaller and smaller and smaller, to the point where you get nothing done, and you maybe have really high efficiency, but nothing's happening. And yeah, 99% efficient to do it. It sort of reminds me of a brother-in-law. He's learned more and more and more and more about less and less and less and less until now he's the world expert on almost nothing, but he is the expert. If you had a small pressure ratio, and then you have to add a bunch of heat to get it up to that whatever limiting temperature was, and then it expands just a little bit, and then you have to cool out a bunch of heat, you get to the point where no work gets done also. And so low pressure ratio isn't good, high pressure ratio isn't good. It's sort of like the three bears, too hot, too cold, and just right. There's a definite optimum pressure ratio for the conditions you want. You design an engine differently if you wanted supersonic than if you wanted high efficiency thrust for commercial things. So pressure ratio is very sensitive to, and even with a given engine, picking the point where do you want to maximize the power output, or you want to maximize the efficiency at the expense of power output. So ideally, you can probably change that. At takeoff, you want maximum power. So you're only doing it for 10 minutes to get up to altitude. And then if you can change the characteristics, you can run a cruise at maximum efficiency. You don't need the power then, and within limits you can do that. Same thing with your car. If you floor it all the time, you're at a stop sign and light changes. Do you floor it just because the light changed? Some people do. It's costing you money every time. If you just sort of ease off, or if you power up to stop signs and then mash on the brake, you can get there. You can get to the stop sign faster. Yeah. But if you block away, you back off on the gas and you kind of coast up to it and let air resistance and tire resistance slow you down, you save on fuel and brakes, and it's all on how you operate the equipment, whether you go for efficiency or power. So there is going to be a unique pressure system that gives you the best either efficiency or power, even if you have, you designed for it, but there's a lot of variables you can put into it. Interesting thing on a gas turbine, the amount of work of the compressor can be 1/2 or 2/3 of the turbine work. Pumping gas is like herding cats. I mean, trying to compress it, it's kind of trying to leak around things, and pushing it forward, it wants to push back, and it's hard. You just gotta, it's like you're always trying to push it that way, and that takes. And when you do move it, unlike water, if you do manage to compress it, it gets hot, and that part of your energy went into just heating it up. So turns out the first gas turbines needed engines to keep them going, and they were like, wow, we only need like 10% of the power output of the turbine to keep the engine going. And that means that the compressor was taking 10% more than the turbine was actually putting out, and that was all in design of blades and things. So anyway, yeah. We'll take this up a little more next time.
Has an hour?
Yeah.